Yeah. Hello, Krishna. I'm audible.
Yes.
Krishna. Okay. So, look, Krishna, we have done this chapter a lot. Okay, so yeah, we have covered the magnetic force and some current carrying wire. Right? So, I just wanted to know, like, do you have any doubt the topics we have done so far?
No.
Krishna, doubt? No doubt. Right? Okay. So, let me see. Okay. So, either like there's one thing I have to discuss, either you can call this a problem or you can call this as some subtopic itself. So the thing is, I want to discuss this. Yeah, magnetic force between two wires kept parallel. So here, when I'm saying this, I can actually conclude two things. Right? One thing is, I have one wire, I have another wire. Makes sense. I'm saying the wires are infinite. Just take the wires to be infinite. Right? Just think of it as an infinite wire. Yeah, just to be infinite. That's the case. So now what you can say is, assume the current to be I1 and current to be I2. Now you will say, like, we have actually two cases. In one case, the current is in the same direction, like this. And another case is, current can be opposite direction, right? So, Kate, now, although I'm going to solve the whole thing, my question is, what do you think? I'm not asking you the value for this right now. I'm just asking. I'm just curious to know that will these two wires are going to repel each other or they are going to attract each other in this condition, in the given condition. Now just think, put some logic. Okay, I'm not looking for the correct answer or something. You will just let me know about the direction, like how it's going. Okay, will it be repelling? Will it be attracting or something? So that's my question for you. Did not tell me first, you have to move to the derivation part or this the solution of the problem. What will happen? Okay, assume that this wire is the first wire is basically infinite. Let's call this as infinite, and assume the other wire to be the finite length. So this time also going to be the finite length. Another wire to be the infinite. Then what will happen? Let's see. Yeah. So in this case, this is infinite. Infinite this side also. Here this is finite. Length L. Okay. And this is infinite. Then I wanted to ask, will it be repulsive? Like what are the forces will be repulsive or attractive? So how even the force will be there? I don't know. Like, okay, let's see. You know that we have studied just now that if you put a wire, okay, if you put a wire in a magnetic field, what will be the force on that? We have seen that force will be nothing but whatever the magnetic field is there, sorry, whatever the current is there, that L cross. What is this L? This L is basically the length of the wire, and this B is the magnetic field, right? Okay, yes, that's fine. But I'm also curious to know that how we are supposed to solve this. And where is the magnetic field? I can see a wire, but I don't have a magnetic field. Yes, it is there. How? Because a current carrying wire has magnetic field around it, right? We already know this magnetic field around it. How it is around it. How it looks like. If this is wire, this is current, then magnetic field will be like this. Okay, for each point, something like this. This point also for every point we will be having magnetic field. Although the value of magnetic field actually differs because for this point, magnetic field at this point at some angle theta. Okay, so if this is a wire finite, then we have to think in another way. But if this wire is infinite, what will happen is due to this point that at this point if I took the magnetic field had this kind of component, right? Something like this. So one get resolved, but another get as it is. So basically, you can say you will be having magnetic field at a line constant. Okay, when it is a infinite. At each line, at some distance r, you will be having a constant magnetic field. So this is one thing I got to make sense. So what is going to be the direction of magnetic field? Let's see. This is current on the first one, right? How magnetic field will look like? The magnetic field will look like this. Okay, at this distance r. Okay. I don't know what's the direction. So you can say one thing that what is the direction of magnetic field? So you know magnetic field is nothing but mu naught by 4 pi, right? Current I dl cross r. This is the thing, and r cube you can just. I'm curious to know only about the direction. So b is directly proportional to dl cross r. Mean to say, if I'm saying due to this wire, this length, what is the distance? So you can say this is one point, this is another point. So what is the direction of magnetic field you are going to get at that point is that will be inside. Okay. At this point, the direction of magnetic field is inside. Understood? Is that clear? Towards the plane. Okay. You can also simply use the right hand palm tool, which I already had told that simply just put your hand thumb tool along with this direction of it. The rest of the fingers will be pointing towards the point which where you wanted to calculate magnetic field. Wherever your point palm is showing. So if you actually do it by your hand, the palm will be pointing inside the plane, inside this plane. Okay. So you can say this kind of magnetic field is. So if I actually wanted to write this thing in something like in some x's. So you can simply say, so upper this, I'm taking this as x. Okay. I'm taking this as y. So this outer axis will be z. Inner inside something going inside will be minus. Okay. So here you can say the B is magnetic field is nothing but B times of Z. Okay. Negative of Z basically. That's the thing we are getting right now. Also, force is mutual, right? Whatever force this wire 1 is going to apply on wire 2, okay, I can simply write this as force due to wire 1 to 2 will be equals to negative F of 2. Okay. This is what we okay. So this is very clear. Okay. So even if I ask you what is the force this wire 2 is applying on wire 1, actually you can't calculate because the wire is infinite in this case, right? If you go and take, let's say this is the point you are calculating due to here to here, here. It will be very difficult for you. Okay. Instead, what I can actually do is, I know this wire is infinite. Okay, due to this wire, the magnetic field is actually just inside. We don't have to do a lot of things about the angle. So just calculate force from 1 to 2. Okay, force on 2 due to 1. If you calculate this thing, what you can say is just simply put like this. You will get the answer for this. Okay, this is one thing. So let's calculate force on wire 2 due to 1. So what you can say is magnetic field due to 1 at distance r will be nothing but distance r is going to be what will be the value of the magnetic field? Here I have already taught you how to calculate magnetic field of infinite long wire. You have already calculated this thing, right? If you simply go by using Ampere's circuital law, what does that law say? That B dot dl is equals to mu naught r, right? So Yes, I think you can actually go. So magnetic field from here comes out as mu naught I divided by 2 pi. But this, if you are not clear with this formula, okay, I have another way. The real formula, ampere circuit law is the easier way. What was the real formula? Mu naught by 4 pi current I dl cross q. Because sorry, the radius because this L is upside, R is down, so the angle between is 90. So cross product will come out as so cross product here will come out as dl divided by R is there, R cube is there. So if this is going to be cancelled out, mu naught I dl divided by 4 pi R. This is what we are going to do. But if you see carefully, this is non-integrated form, right? So when you just go and take the whole integration of the around the circle, again you will be getting 2 pi r. This is just going to cancel out and something like that. So basically, at the end of the day, the formula which we are going to get is this. This is the formula. Okay, so I'll just put it over here. So B mu naught I divided by 2 pi r. And what's the direction? Again, because magnetic field is inside. Right now, I'm calculating here, not here, because when you calculate here, the direction will be outside in the z direction. Okay. So here, currently, where my wire is fixed, the direction of magnetic field is negative of, okay, something like this, right? Or in another way, what? Let's go with the magnet, okay? Because we know the direction by ourselves. Okay, makes sense. So what is the force? Now the twist comes up with the force. What is the direction of force? Okay. Magnetic field at this point is inside. The wire is kept like this. So current is going in this way. Makes sense. What is force? Force is nothing but L cross B. L is upside, B is inside. So what is the direction of force you are going to get? This. This is the direction of force value. Is that clear?
Yes, sir.
Okay. So this is the value of force you are going to get. So if you see carefully, what's happening over here? So magnetic field is this. What is the force? I. Again, L cross B. L is upside, B is inside. Both are perpendicular. So L cross B will also become LB. On the sine 90 degree will be. Yeah, Kirtana, can you hear me? My screen was actually lost. So, yeah, Kirtana, can you see the.
Yes, sir.
Yeah, okay. So we were discussing about. Yeah, okay. So here we were. I makes it. I don't know what is the value. Okay, so here if you see carefully, I have current now. What is the current? What is the force? Force is basically current. Right now the current is I. So simply put I2. What is B? L. L is basically a complete length. You can put as L. What is B? Again, B is this much. Mu naught I. What is the current? Here the current is I divided by 2 pi r. So what's the formula you are getting? Mu naught I1, mu naught I1, I2 L divided by 2 pi r. This is the formula you are getting. Okay. Acha, what's the direction? Towards the wire. Understood? Towards the wire. So one note you can actually go with. Okay. If I ask you what's the force, this F1, okay, this force on um, 2 due to 1 is mu naught I2 by L 2 pi. Okay, ladies. So force on 1 due to 2 is negative of F, okay, which is nothing but minus mu naught I1 into L by 2. Now you will say, sir, why this? What this negative suggests? This suggests that generally when we solve the problem and we are seeing negative positive is basically for the sign convention. So this wanted to suggest that whatever the force you are getting on 2 due to 1, right now due to 1 to on 1 due to 2 is basically the opposite of that. Okay? If the force in that case was this, so here it is this. Okay? So point you can actually note it down is if wires are parallel and current in same direction, current in same direction, then what I can say that F magnitude will come out as mu naught I1, I2 L divided by 2 pi. You know, that's the one thing you are going to get. This is case when one of the wires is one. Also, nature is attractive. Okay, will attract. So, if you go in a similar fashion, similarly, if current is in opposite direction, is opposite in direction, then what will happen? They will repel. Okay, then F will still be the same thing. Mu naught I1 I2 L divided by 2 pi R. Just the nature will be repulsive. So repulsive. Okay, I'll just show you how. So if I just go back to the top, what I said is here you can see my current was upside. Here also my current was upside. So basically what happens is when you put L cross B, assume right now magnetic field due to this one you have got in this way, right? Where you have got inside. Magnetic field will stay same, but right now instead of this direction, now you have got this direction. So magnetic field inside, you can call this as minus Q. uh, this L is basically downside. You can call this as minus 1. So this thing got you as y cross k. What is y cross k? Basically y cross z. Why cross z? Why not minus? Because negative, both of them are negative, right? So this will land you I. What is I direction? I is this side. Understand? So that's how it is changed. When your length was upside, it lends you minus. Okay. So that is the only difference. And the same will observe. You can observe with other cases. So, Krishna, let me know if you have any kind of doubt or something. If you are clear with the thing, we can move next.
No, no.
No doubt, right? Alright, so Krishna, look, let's move to one problem based on this. For that, you should be very clear with SHM. So, are you clear with the SHM concepts?
Yes.
Okay, makes sense. Then, I can actually give you one problem. The problem is, here, Krishna, you have infinite wire. Okay, this is infinitely long wire. So, what happened over here is, there was a another wire having some small length L. The length was L, and in this case, the current was I1. Here, the current was I. That kind of thing was there. So you know very well because the direction of current is opposite, they are going to repel each other. Because I have kept this on the ground, I have kept it on the ground. It means if you have kept this on the ground, it can't go anywhere, right? You have maintained it at some distance h. So first you have to tell me what is the distance h. Okay. Can you tell me this distance h? Assume the mass of this whole rod is m. Okay. And it is under the gravity. So m and g is also present. So you have to tell me what is the mass, what is the height. Okay. What is this h on which it is balanced? SHM I'll come up later, but for now you just let me know the distance. Calculate the value. So just solve it and get me the solution for this. Krishna, you are trying the problem.
Yes.
Okay, so just do it fast because we have a lot of things to do. Uh, this part I can solve it here. After this, another part will be what if I give it a small displacement at this point? Here, if I give it small displacement up and down. Okay, so what will be the time period of frequency you have to calculate? That is what that I'll keep it as another part. Krishna, have you got the solution?
I'm trying.
Okay, do it fast. Should I give the solution, Krishna? Krishna, do you want me to solve the problem?
Yes.
Okay, fine. So you can have told me earlier, right? Alright, so look it now. Remember, okay. So what the question is saying that you need to get the value h at which it is balanced. How it is balanced? Let's see. Let's say this is a wire. Okay, I'm making a video of wire. Let's call this is wire one. Okay, wire two. Let's call it this. And here this is wire one. This is on the ground, right? On the okay, makes sense. So if I just go and make an FPD of this wire two, so how it will look like the wire is there, okay, makes sense. Current is going this side, makes sense. Before this, let's okay, you know that the current we have already discussed the force and how to calculate everything in the previous, so I won't discuss it more. You know the direction is opposite. It means they are going to repel. Repel means to say this wire is going to apply force on this. This wire is going to apply force on this. Makes sense. But this wire is on this table itself or whatever you can see the ground. It is not going to move. Okay, what will happen then? Here, this wire is going to get a magnetic force. Due to from there this is going to get this is going to get it due to Fm1. Okay, from wire one it is going to get force. What will be the value force? We have just seen now mu naught value force current I1 into I2 multiplied by length of it divided by 2 pi, and here it is basically the distance, right? Here we keep r, but here I wanted to calculate h, so keep it over h. Okay, this is I wanted to calculate, makes sense. So here the force is upside, F and what force due to. Also, what is there any other force? Yes, there is something called gravity. It is mg dot. So anything else is zero. If it is balanced, then Fm1 should be equals to mg at h1 balanced. Okay. Now I think you must have got the answer. Just you have to put this thing, right? We have already got the value of this. I1, I2 L divided by 2 pi h mg. So what is h? Mu I1, I2 L divided by 2 pi mg. That's the small formula. Is that clear?
Yes.
Okay. So, Kirtana, this is the formula I'm getting. That's fine. What if I just go and do one thing because you know this is balanced, right? But it's not just confined. What I can do is I'll go. Wait, I'll just put. Let's see the full form. Okay. Yeah. So assume this is my case. This is wire, and I have another wire. This basically is going to tell you the path. So if I just that's the path. If I just go and get the upper one, you can see what if I'm going to do. I'll just go and do a small displacement like this. Very small displacement. Okay? I'm going to get a small displacement. You can call this as x from the main position. Now because this is balanced, you can call this as the main position, right? And here you had a bottom, another y, infinite. So yes. In this case, if I give this condition, because you know I will give a small displacement upside. Okay, I will leave it. What will happen then? It has some. There's a force on it, right? But because it is at some distance, so there's some potential on it. What is the potential? You can actually go and calculate that. We'll see it after that. Also, there's a force downward. It will when it will fall from this position to this position. This is a balanced position, right? When it's going to fall it from here to here, here the velocity is zero. Initially is zero. Because it is falling, it will gain some velocity. What is that velocity? That's it. That will have some value. Okay. It will come up here with some velocity. It will go a little bit downside because whatever the potential it got here, all is going to convert here as a kinetic. Now this kinetic is going to get converted back as a potential here. It will stop here. Because there's upper side force and it will again start going upside. Here it will again this thing will go on forever. Because we have not assumed some air resistance or something, right? So your task is to calculate the time period of this. Okay, what is the time period? So can you do this, Kirtan?
I'll try, sir.
Okay, you could try, right? So yeah, this is I'm actually not solving it now. I wanted to give you some homework. If okay, for this I will suggest if you're not aware, you can just go through the SHM concepts once. Okay. Yeah, if you are not able to solve it, just let me know in the next class. I'll explain it once. Okay.
Okay, sir.
Okay. Now, yes, before moving to next, I would like to give you one more problem. Actually, you can take both problem as well. Okay. Do I need to write that problem here now?
No need.
No, right? Okay. Another problem here is this is an axis. This is not y or something. This is x-axis. Let's make it dotted. This is y-axis. Let's make it as a dotted line. Now, what I'm trying to say is there's some magnetic field. Here, this is y-axis. Here, this is x-axis. Here, the magnetic field is inside, okay, coming outside from inside to outside. But the value of magnetic field is B naught times of x. Okay. It means what I wanted to say is your value of magnetic field is increasing. For example, if you put x is 0, when you are at x is 0, at the whole line the magnetic field is 0. When you move to some value 1, maybe x is 1, here when you put it will become 1. So here magnetic field has some value. When you reach it, it's this kind of thing you are going to see. Understood? But and also I'm saying there's a wire which I have kept at this point. This is a wire. So this is a wire I kept at this position. Okay. Yeah, this is x0. This is x is equal to length. So you can get to know the length of this wire. Your task is find out the net force on the wire. The net force on the wire. Okay. That's what you need to calculate. At this instant, if I just wanted to know at the instant shown in the figure. Instant. Because I'm not asking you what will be the acceleration or something, because you know force is there on this wire. Here less force is there and more force is there. So it will actually move. It will actually move, right? So this is what you need to calculate. So yes, Krishna, just try it once. Or if you want to take it as a homework, you can also take it. Because if it would be the case, I would move to the next topic itself.
I'll do it as a homework.
Okay, you'll do it as a homework. Okay? So two problems are there. One is variation of the first problem. Okay. Yeah, one will be the variation of this first problem. I think you know what you need to do with that, right? I have not written over there. Another is this one. I will say this part is quite easy for you as compared to the other one. This problem is going to be easy for you as compared to the next. Okay, so let's move to the next topic. The topic is torque on the frame, torque on the loop. Kirtana, today I won't take till 9:15. Okay, I may be taking it just to 9:05 something. 10 minutes early I will end the session. Yeah. Okay. So here the calculation we can go with. So let's talk about force and torque when force and torque. Torque on current carrying load. Okay? These two things we have to calculate. Loop mean to say a loop can be square, a loop can be circular, whatever you are want to say. Okay? But this will be carrying some current. Okay? So what I wanted to say is I'll be basically saying is like this kind of loop you are going to get something like this. I'm saying current is flowing, so it might be like you can say the current I is flowing over here, current is I is flowing, I is flowing. I is going, so this I is going and I is going. This kind of current is going to, okay, make sense. From bottom to upside, you can say there is a magnetic field, okay, makes sense. Magnetic field is also there. So yes, if the current is there, magnetic field is there, you know there will be force on the wire. Okay, what is the direction of the force? In this particular case, if you take this component of the wire, this portion, this small portion of the wire, here the length you can call PL. Magnetic field upside, this is upside. So magnetic at this point, the force will be inside, right? Force will be inside this side. Okay, if you talk about this thing, the length you have taken this, magnetic field is this, the force will be this side. Understood? So these kind of thing will be there depending upon the situation you are given. So most cases, if you see, it depends upon the angle of B and this, right? So we are going to take a very general case. Now assume that I am saying instead of this way, the magnetic field is inside. It is going inside. Okay. If it is going inside, what will happen? Uh, Assume this to be signal plane on the 2D plane. Okay, like this, current is going this way. So magnetic field is inside, right? This kind of thing is there. So we are going to take this small length. Okay. Magnetic field is inside. Okay. What is the force on this? What will be the force on this field now? Okay. What is going to be the direction of force on this? If I'm saying this is magnetic field getting inside the plane, okay, there's a wire having current like this. So if I small take this component, what is the force on this wire? Upside, right? Force on this will be upside. Yes, it will be upside. Okay. On this, if I ask what is the force, yes, so that is downside. Makes sense. This kind of force is going to be there. This is one thing very clear. But what about this case? What about this case? Okay, wait. I don't know what is this case. It is just downside. It is like left, right, up, down. This kind of angle is there. Here, if you see, this length can be taken as two directions. One is downside, one is this. So here, if you see, magnetic field is downside. Current length, okay, length portion is actually still perpendicular to the magnetic field. So what is going to be the force direction? Force will be outside. So you can see each component, each part. If you go and see, the magnetic field is outside, it's coming outside. Is that clear? So I can simply say if I go as take small component, sorry, yeah, I'm going to take this small component having length dl. So what is the force on this? df will be nothing but current is same in the whole loop. What you are left with dl cross. This is something you are going to get. Makes sense. So what is the net force you are going to get? Net force is F is going to be integration of dl, current is there because current is also P is also constant, right? So what you can simply do is to do this kind of thing you are getting right now. So if I ask you what will be the yeah what will be the integration of the whole length? You know that if you just join this thing, right? Then you join this thing. When you join all small components, what is the length you are going to get? Complete length where its force will be nothing but B times of I times of L. This is you are going to get. In more formal term, if I want to write in the this way, you can see this. Now you will say, so what's the difference in this? What's the difference over here? If I ask you what is this case, do you think this integration is correct here? What do you think, Irma? This integration is correct or not? Uh, Please be vocal in this.
Yes.
No, it's not. If you could remember in the previous session also, I told you how the case is ongoing. I'm just making this kind of thing. I told you what you are doing is we are taking a very simple. I took this small link. I said this is my right. Now I am saying you have to do integration. What is the integration? You are doing vector integration, right? It means you are adding all the this, then this, then this, then this. Wait, do we have seen this? Yes. In the polygon log vector. Vector A, vector B, vector C, vector D. How we solve it? Basically, I say what is the resultant of this A and B? This is this. Okay, makes sense. What is the resultant of this and the whole thing? This. What is the resultant of the whole thing? This and this. So it will be this. So the resultant of the vector is nothing but starting the distance between basically starting and ending point. Okay. Here, what is the starting point, ending point? It started from here. It ended up here. So can I say when you do this thing, when it started from here, when it ended up here, can I say the net force is going to be zero? Yes, it is going to be zero because this integration is going to be zero, right? So that's why the integration we have to keep it as zero. Okay, this is one thing to be care about. In another word, if you wanted to say, you can see force on this portion is upside, force on this portion of the wire is downside, force on this is this side, force on this is this side. So similarly, in each component, each of them are going perpendicular this way, perpendicular this way, perpendicular this way. So if this is a constant rigid body, you can say the net force is all direction. You can actually make it like this also. Vector up, vector this way, vector this way, vector this way, vector this way, vector this way. Now, what is this? This is nothing but force, right? F1, F2, F3, F4, okay. If you add all of them, the resultant is zero. Why zero? Because the magnitude of everyone is zero, okay? And they will must be having some same angle, okay? They will be nullifying at all of them at the end of the day. This is a small vector concept I have taken. So the force is zero, makes sense. Force is zero, null, null vector. Makes sense. So then what we have to calculate next? That is torque. Torque is important. Okay? So what I'm going to do is force is zero, not torque. How to calculate torque? Let's see. For torque, I can actually have some random shape, but I'm taking some regular shape. Instead of random shape, I'm going to take regular shape. So this is nothing but a kind of circle we can see. Okay. Or let's do one thing. Let's not take the circle. Let's take semicircle kind of thing. Something like this. Complete semicircle you have to take like this. Now in this complete semicircle, current is I, current is I, and current is I. The current is I. Okay. What we wanted to calculate, we wanted to calculate torque on this road. How we are going to calculate this? Also because this is semicircle, I will say this is a pointer. So this distance is R. So this is also R from this side. So here you are going to keep a magnetic field. What is magnetic field? Magnetic field is parallel to it in this. So what is going to be the loop? What is the formula of the loop? Makes sense. I don't know. Even though the force on the net loop is going to be zero, because you can say it's a closed. Even you can say a closed surface is there. If you go and place that into the magnetic field, the net force on that loop is going to be zero. So if it's a closed structure. If force is zero, does it mean that torque is also zero? May or may not be. Okay, let's see. Right now, if I take this portion of the wire, okay, direction is this, magnetic field is this. So L cross will be zero. On this wire, the magnetic field is zero. What about this? Here, here the force is nothing but it is in some angle. Okay, it is at some angle. What is the direction of force? That will be outside towards me. So you can see rest of the portion except this part which is directly parallel with other part which is like this. Okay, all these parts have some force. What is the direction of force? Towards me because you can see magnetic field. The length is either you are taking this, either you are taking this. Magnetic field is like this. Right? So you are going from this to this, parallel to inside. So what you can say now that magnetic field on this part is inside. Magnetic field on this part is outside, coming towards you. Okay, makes sense. What about this part? Magnetic field on this part is also sorry. Um, yeah. Okay, wait. If you see carefully, what about this part? This is anti-parallel. Anti-parallel means to say angle is 180. Sine 180 will come out as zero. Understood? So you can say the portion which is parallel to it, okay, which is parallel to this, will provide zero force. Okay. The rest are the two are going to provide force. But if you see carefully, I can actually divide this semicircle into two halves. What are the two halves? Up and down. Okay. If you see, this half is trying to push it towards me, towards me. Okay. This part is taking me towards outside. Sorry. It is coming towards outside. It is coming towards inside. Okay, makes sense. Isn't it looking like the condition light? Okay, now I'm trying to see it from this side. So what I will see that there's a small length of wire. It's not small length. I just wanted to give you a brief. Okay, I have divided from this part. On this, the force is inside. Basically, it is coming outside. So outside, I'm making like this. Here, the force is coming outside. It is coming outside. The intensity is different because here, if you see, as the wire goes, angle is increasing. So because the B and length is same, angle increasing, force increasing. Mean to say, more the outside, force will increase. So if I wanted to make it like this, something like this. So the angle is actually like this. Suppose here is like this. Okay. Why here is like this? Because the shape is very irregular. When shapes are regular, the forces will be symmetric. The whole thing will be equal. Okay. Because here if you see it is not. Makes sense. So if I ask you what is the net force? F net is nothing but upside this much force. This is equal to this. So F up minus F down. Both are same in the magnitude. So this is given 0. F net is 0. But is the torque 0? I will say no. Because about this point, what is going to be the torque? Torque about this point O, what is the torque value? If you go at some distance R, force is upside. So let's talk about d delta t. Due to this, what is that? R cross F. Yes. This is the force here. Okay, what is the force? This force coming up due to the L itself. I can say L cross. What is the force? L cross T. This is what I'm going to get told it. Any doubt, Ketan, here?
Yes.
No, right? Okay. Further, can I write something else over here? Yes. If you see, can I write something else over here? Okay, so you can see these kind of thing is that we need to integrate this. If I just go and integrate this thing, I am going to get some value of torque from here. So you can say that torque is not zero because we have some value of R, you have some value of R, you have some value here also you have some value of R, you have some value. Here the torque is towards me. If you just apply due to this, here R is this side, F is upside. What is the direction of torque? Towards me. Here, R is this side, force is downside. What is the force direction? Outside. So net torque is basically towards me. Okay, the torque has some value. We are supposed to calculate the value of the torque. So can we do and calculate that value? Yes. This torque part, Ketna, like the derivation for this torque part, I'll try to go try to explain in the next class. Okay. Yeah, I have to take the session till only this angle. Or I can actually explain it a little bit more. Okay, let's cover the whole thing. Right? So just let me know if you understood the main concept here. That torque is not going to be zero. Now we are going to calculate actual value of torque. I will take this area, basically this shape, and will calculate the whole. Okay, makes sense. So create now look, this is a point. Okay. Due to this, the hole is carrying current I, current I, carrying current I. At this point, I am going to take at some angle theta from bottom. I am taking small angle, a small length dl. Add some angle theta and d theta. This is what I'm doing. So if I ask you what is the torque over here, you can see here my magnetic field is in this direction. B. So we can simply say, sir, that the angle between them is like this. What is that angle? I don't know. Because this is perpendicular to it. Yes. If it is perpendicular, this is 90 degree, this is 90 degree, right? If you extend it little bit like this will be 90 minus theta. Something like this. Or you can also say that what is this angle? What is this angle? This is going to be theta. So what is this angle? This is 90 minus theta. So that kind of thing you are going to get. So simply you can call this angle as 90 minus. That's what we are going to do. So let's remove it for now. At some angle theta, you are going and creating d theta. So what is the net force? Force we have already seen that is going to be 0. I wanted to calculate net torque on this loop. Okay. So how I'm going to calculate that? That's my main task. So if you see here, at this point, my torque is coming out. What is the direction of the torque I'm going to get? Sorry, the torque I'm getting outside. Okay, makes sense. So d torque I have written as what I have written over here. Wait, the force. Okay, and the distance. What is the distance over here? Look, you know the torque I'm going to take with this loop, right? So what is this distance from here to here? You can call this as r cos theta. Okay? This is r cos. So your formula for the torque basically comes out as r cross f, which comes out as uh, yes, r is basically the radius times of cos theta times of force df. Okay, small force. Makes sense. What about this part? If I go and look at this, if I look at this point, okay, this is a small theta. Okay, from which angle I have taken it? I have taken it from this theta. So this also becomes because of this. This is the radius, so this is r cos theta. Force here is inside. Force here is inside. Okay? One side it is outside, one is inside. This is inside. So what is the torque over here? Torque will still be the same. Torque will still be the same. So you can write it two times. So the net torque comes out as 2 times. Now, how you have to go integrate? You can integrate this from 0 to 90 degrees. Here also 0 to 90 degrees. If you do this, you will get the net torque. What is the net torque you are going to get? Just integrate this. So tau is equals to 2r cos theta. But what is the value of force? This is nothing but I am unsure of this force, so I need to put the value. What is that? I current, magnetic field B constant. Sorry, this is L cross D. Okay. What is the value? I have already given you this thing that this is nothing but theta, right? That value comes out as cos theta. So because 90 minus theta, cos theta. So 2r cos theta dot IL. What is the small angle between DL and this thing? I have shown you this is 90 minus theta. So when you're going to put sine 90 minus theta, that will become cos theta. This is cos theta. Makes sense. What is DL? You know that this is d theta small angle. This is length L. DL basically. So we know if this is the radius r. So DL is equals to r d theta. Okay. So just put that torque. Torque is equals to 2r cos theta dot I. Instead of dl, r times of, make it square. Cos theta is there, make it square, both of them. Instead of dl, write d theta and b you put outside. What is top? 2b r square cos theta is variable, keep I inside. Cos square theta dot d. That's the integration we are supposed to. Okay. 2I dr. So what's the integration of this thing? You know that the cos square theta can be rewritten as in one term as um, 1 plus cos of 2 theta. Okay, how? Because cos 2 theta is written as cos square theta minus sine square theta. Okay, if you put the value of cos theta as 1 minus sine, okay, if you put this value of sine square theta 1 minus cos square theta, this becomes 2 minus 1. So this we just need this part. So this thing will be like this. Okay. That's the thing we are going to get. Just go and put cos 2 theta by 2. But here if you see I have theta, cos theta, right? So here I can actually go and put the value of theta. So this becomes 2b r square I in integration 1 by 2 plus cos 2 theta by 2 d theta. You know this is just a constant part, so it will go from where to where? 0 to pi by 2 it is going. Okay, it is going from 0 to pi by 2. 2b r square I from where to where it is going? Pi by 2. Plus from here to here. It is going as pi square by 2 square, so that will become 4 square basically. and half is itself there. So this you can just put that half outside, so it will become cancelled. It gets cancelled. Plus about this part, this is cos 2 theta. So if you just go and solve this again, what you are going to get? Sine of 2 theta divided by 2. There was already theta, but I'm not even bothered about that. So sine 2 theta by, also this theta went up from 0 to pi by 2. You can see when you put the 0, still the answer is 0. When you put pi by 2, still the thing is 0. Okay. So the whole thing will actually come out as b r square I pi square by 2. This is what I'm going to do. Any doubt? No. The reason is here you should actually, this is incorrect. The integration, this will be just theta. So here it should not be square, it will be just 2. Sorry. Yeah, that's the thing you have got. So you can see now pi by 2. If you see carefully more further, I can write this is I. Okay. What is pi? R square. Pi square R, because this I have taken as a semicircle. If you just go and take the complete circle, this will become area of a circle. Because it is a division by 2, so you can call this as the area of semicircle. Okay. So here, the thing is basically I into area of semicircle multiplied by 2. So the formula for the top comes out as b I times of a for any regular shape. For any regular shape. For any shape. Okay. I will give a derivation for this, although I have taken here some regular shape. But in the next class, I'm going to give you a complete overview in some random shape. Okay. So that's the thing. Also, if I wanted to write this in a top form or something, this will become I is a constant itself, a cross b. Okay. That's the top we are going to do. And it out,
Yes.
not up, right? So, Kirtan, that's all for the today's session. If you have any doubt, you can let me know. Otherwise, you can message me. So, okay, now that's all. In future, I'll let you know like this I into E is something else. Okay, we'll see about this in future classes. So, yeah, that's all for the previous session. Goodbye.